Welcome to Monday. Remember Lamatre was talking about the hidden God from Isaiah. Says, I will give you hidden treasures, riches stored in secret places, so that you may know that I'm the Lord. Right? So if you think you don't see the Lord, maybe you aren't looking for his hidden treasures. Yes, secret places. And today, we have an opportunity to uncover more of these hidden treasures in secret places. And thank the Lord for that. Yes, is the glory of God to conceal a matter, search out a matter is the glory of what? Kings. And you guys are all what? Kings. Yes. Yes, search out a matter. Yeah. Right. Pretty cool. And here we are searching out matter. Matter in chemistry. Up to here, we're talking about E's and I's and some aromatics and stuff today. Okay? Wednesday, we'll talk about polymers. Right? You have problems, chemistry has what? Solutions. Yeah. And then, in less than 2 weeks, right, because here's Monday, there's another Monday, so about a week and a half or so, we'll have our what? Second test. Yes. Hope you have that on your calendar. Yep, there it is, coming up already. Yep, our second test. Wow. There it is. Okay, so we better get going here so we can cover all this stuff. All right, last time we were together, we talked about some stereoisomers, handedness, chirality. Yes? We talked about geometric isomers with respect to alkenes, being cis or being trans. Remember those? Yes, kind of, sort of. Right? Hopefully that's some mastering chemistry homework there to remind you of those things. And then we started talking about anes, enes, and ines, naming them, their physical properties, and we started getting into the reactions of anes, enes, and ines. And that's where we want to pick up today on those reactions and move on from those reactions to talk about reactions of aromatic hydrocarbons. Okay? So cool stuff. So let's remind ourselves of some of these things. All the hydrocarbons combust. Yes? Here are some combustion reactions. You guys can write these out, balance them up, right? Do the stoichiometry and the CO2 and the water, right? Old stuff. Man, you've been doing that since, I don't know how long. Okay? Long time. Right? Another reaction we talked about, okay, is substitution. Yes? Where what you can see happening here is one of these hydrogens has been replaced with a what? A chlorine. Okay? Here's the chlorine, comes in as Cl2. Heat or light breaks it up. Yes? One of them goes on. The other chlorine takes off with the hydrogen. Yes? Like the cow that grabbed onto the spoon and jumped over the moon. Or however that song goes. Was it the cow and the cat? Who jumped over the moon? A little dog jumped over the moon. Nobody remembers. Okay. All right. Anyway. All right, so that's a substitution reaction. We talked about addition reactions. Okay? Where if you have a double bond, here's your double bond, yes? It can open up either which way, sort of like doors on a hinge, yes? And you can grab on to the chlorines. So here's one chlorine, there's the other chlorine that gets hanged on to. And your ene became a what? An ane. We say we add across the double bond. Right? No catalyst required. Right? They'll just do this. Okay? All right. Pretty cool, huh? Okay? We could do the same thing with hydrogen, adding across the double bond. Yes? So now the hydrogen added here and the hydrogen added there. Yes? And again, the ene became a what? An ane. Yes? Opened up. One bond, made two connections. Yes? And we still have the other bond that was there from before. Okay? Addition reactions, we call these. Yes?
What is the purpose of the hashed line in the cone?
This is to show that it's going back behind the screen.
Oh.
Yes? And this is to show that it's coming out at you. Okay? Tro really got this a little bit bad. It should be a hashed line getting smaller to give perspective. Yes? Somebody messed up in his font testing thing there. The same thing with this guy. Should be a bigger hash line and get smaller as it goes away. Yes? Right? So those are to give you perspective on things. Because these aren't flat molecules, right? Yep, they're three-dimensional molecules. This guy is flat. That part of him is flat. Yes? Right? But once you make him an ane, he's not flat anymore. All right. Here we add HCl to the double bond. Okay? And now you say you got an H and a Cl. Right? Before, when it was Cl and Cl, or H and H, it didn't matter which one went where because they were both the same. Now it does matter which one goes where. You open up the bond here, there's a door. Open up that bond there, there's a door. Now who goes here, the H or the Cl? It looks like the H went there. Okay, and who went here, the H or the Cl? Looks like the Cl went there. So how do you know who goes where? Well, look in the beginning. How many H's do you have on that carbon? 2. How many H's attached to this carbon? 1. The rule is, he who has gets more. The rich get richer. Okay? So if you are already rich in H, you get the H. So now how many H's are attached to this carbon? 3. And how many are attached to that carbon? Still 1. Yes? Markovnikov's rule. The Russians. They want to make the rich richer. Yes. So there we go. All right, and that brings us up to where we are here. Questions on any nomenclature or reactions and stuff like that? Yes. Oh, just stretching? Okay. Yes.
The parts that come off the main molecules. Explain the nomenclature for that.
Okay. Well, things that come off, you guys can name. HCl, that's the formula. You could name it as a binary acid, then it'd be what? Hydrochloric acid, yes? Or you could name it as a molecule, then it would be hydrogen chloride. Yes? Right? Cool. Yep. Good question there. Whenever you see these reactions, you should ask yourself, how would you name these things? What's the name of this thing?
2-methylethene.
Well, yeah, you might want to say that 2-methylethene. Okay, but is that the longest chain? 2? Longest chain has 3. So that makes it a what? A pro, and it's a ene, because it's got a double bond in there. So propene. What would you name this thing? 1, 2, 3 carbons. Okay, no double bond, so let's say what? It's a propane, and what's hanging off of it? A chloro. Which carbon? 1, 2, 3. So it's hanging on number 2. So you say it's a 2-chloropropane. Yes? So every time you see these things, ask yourself, can I name them? If you see a name, can you draw it out? Yes? Right? Practice your naming of molecules and stuff. All right, let's try quiz number 10, and we'll see how it goes. Okay, so the first one, draw a structure for 2-methyl-3,4-diethyl decane. Yes? You have to draw that one out. Okay. Somebody made the comment that there should have been ethyl first and then methyl, right? Okay, it should have said 3,4-diethyl, then 2-methyl, but either way you can figure it out, right? Okay, the decane, here's your decane, yes? 10 carbons in a row. And you've got a methyl, a carbon number 2, and at 3 and 4, you've got an ethyl group, ethyl and ethyl. Yes? Are you with me there? Okay. Somebody in the other class said, well, why don't we go this way? Then you could have a isopropyl ethyl hanging off of your decane. It'd still be a decane. Yes? But then you just have 2 substituents. Whereas if you went straight across this way, you get 1, 2, 3 substituents. And the IUPAC names rules are Name it so you get more substituents. I'd prefer it the other way around, but, you know, they like it that way. So you could name it either way, still communicate what you're talking about, right? Okay, the second one, name the alkane drawn below. So some of you might have fallen for the old left to right thing and gone 1, 2, 3, 4, 5, 6 and call this a hexane. But remember that we can do what? Go around the corner and now it becomes a what? A heptane. Okay? So we go 1, 2, this is going to be 3 and 4. So it's going to be a 3,4 dimethyl what? Heptane. Yes? How many got these both right? Okay.
Quick question.
Yes.
Did we have to draw this structure for the first one, or could we have written the carbon hydrogen structure form?
You like put all these hydrogens and stuff on there and stuff?
Yeah.
Yeah, you can. It takes a lot longer though. Yes. Okay. All right. Okay, well let's move on here. Talk about some new things in chapter 20. Okay. All right. More exciting stuff. We're going to talk about the aromatics today. Remember those? Well, the hydrocarbons we haven't talked about yet. We're going to talk about their physical properties, their nomenclature, and then their reactions. And this is going to be a model for us. Whenever we get a new functional group, we talk about these three things: physical properties, nomenclature, and reactions. Yes? So, we're going to do this for the aromatics, and then we're going to go more quickly through the other guys: alcohols, carbonyls, ethers, and amines. Okay? All right, and you'll get the sort of idea here as we go. So here's the aromatic, benzene. Okay, there's a benzene molecule floating around here somewhere. Earlier, anybody have it? No? Did it come back to the front? No, maybe somebody walked away with it. Huh? Oh, here it is. Somebody brought it to the front. Here's the benzene molecule. You can see that it is flat. Yes? Alternating double and single bonds. Okay, you can put the single bond here, or you could flip it and put the double bond there. And in fact, you can't tell the difference. It looks more like a 1.5 type bond. And it's flat like a frisbee, such that if I took it like this, it would slice right through you. Yes? Because, you know, it's like, you know, one molecule thick, or one atom thick here. Yes? And so, you know, it sliced right through you, in through your cell membranes, into your mitochondria, all that other stuff in the cells, sliced up your genes. Yes? You'd be in a bad shape. In fact, benzene is everybody's favorite carcinogenic molecule. Yes? It's everybody's, you know, example of bad molecule. Right? So you shouldn't go around wearing benzene on your head like that. Yes? All right. He's got very good posture. Look at that. All right. So, there it is. Okay? So, sometimes we say that there exists this sort of cloud of electrons around this entire circle of the benzene molecule. Yes? And that's what gives it its functionality and also stability. Okay? Because it's a happy molecule that way. Now we need to name the benzene. So we talked a little bit about physical properties. Now we need to name these things. Okay? So if we put a fluorine atom on benzene, we call it what? Fluorobenzene. We put a propyl group on benzene, we call it what? Propylbenzene. That's pretty easy. Okay? So that all seems fine and dandy. Now you might think that this should be called methylbenzene. Yes? And that would be a very proper thing to call it. But for the fact that it was known as this other thing long before, it was known as toluene before people knew that it was in fact methylbenzene. Yes? And so this name toluene has stuck, kind of like Bailey has stuck. Right? It's Bailey, right? Is that right today? Okay. Yeah. All right. So there we go.
So would it still be okay to call it benzene?
Well, you could call it methylbenzene, but if somebody calls it toluene, we need to recognize that it is this. Yes? And so you need to know both the common name and the more systematic name. Just like you guys have a name and you have a floor name. And you need to know both of your names in order to operate properly on campus here, right? Here's another one, aniline. Okay, it's got this NH2 group on it. Phenol has this OH on it. It's funny, you know, sucrets have phenol in them. Yes? But benzene by itself is a carcinogen. You'll never have a sucrate again, right? Just replace the hydrogen with an OH group, and you got a sore throat lozenge. Yes? But it's just one atom away from being a carcinogen. Yeah, benzene's carcinogenic. You don't want to suck on cancer-causing things, right? Wow. You better get your naming right here. Yes? You'll be in bad trouble. Styrene. We make polystyrene out of this. Yes? Stuff like that. Peanuts in your Amazon boxes, right? All right, let's name some benzene. Let's say benzene is on a big, long hydrocarbon chain. What do we call it then? Well, we don't say this is for benzyl 1-hexene. We say it's for what? Phenyl. Yep, benzyl is actually something else. So this benzene ring that you might think should be called a benzyl group is not. It's called a phenyl group. Yes, that's a bad thing, but that's what it is. Okay? So this is 1-hexene. So here it is, a hexene, 1-hexene, and then at carbon number 4 is the phenyl group. Okay? Just like if it was 1-hexene 4-methyl, or 1-hexene 4-ethyl. Now it's 1-hexene 4 what? Phenyl. Yes? Okay. Pretty cool there, huh? Yes? All right. Okay. What if we have two things attached to the benzene ring? Okay. We had just one, we'd call it bromobenzene or fluorobenzene, but now we have two of them, and we have to indicate where they are on the ring. So we have to start numbering the ring now. Yes? Okay, who gets the lowest number? The first one, the alphabet, right? So it's 1 bromo, 3 what? 3 fluoro. Yeah. There's the bromo, there's the fluoro, and they're all on the benzene. So here the benzene is the parent again, because it's the big thing. Okay? Now here, again, you could say this first thing would be methylbenzene, right? If you wanted to say it that. Or methylbenzene. But now we have two methyls, so it's a what? Dimethylbenzene. And it doesn't matter who you put first, because they're the same. So it's going to be a 1,2 dimethylbenzene.
On that bromo, yeah, that right there.
Yep, it's 1 bromo,
Right.
3 fluoro. Yep. Now you might also name this as toluene, and then say this is a what? Methyl toluene. Right? That'd be another way to name it. Multiple ways to name these things, which is unfortunate for you. Okay?
So does that mean if you get one of the three, you're still good?
No, not necessarily. Depends on the situation, right? Okay? So here we go. Naming these things. All right. Now, there's another way to name these same things. Okay? As well. Okay? So here we could go. We could call this one, we could call chloromethylbenzene, right? We could say it's 1 chloro, 2 methylbenzene. Or we could name it as a substituted toluene, where this is the toluene part, and say it's 2 chlorotoluene. Or we have this other little thing that we came up with called ortho, which means that it's on the carbon next to the carbon of the methyl group. Yes? Right? And there's 2 ortho positions, actually. Okay? Here or there. Either of those guys would be an ortho position. Okay? We could say 3 chloro is the same as a meta. So 1, 2, 3. And there's how many different meta positions? 2. Because you could go 1, 2, 3 that way as well. And then if you're all the way across from the methyl group of the toluene, you could say that's 4 chloro. Or we could also say it is what? Para-chlorotoluene. Yes? Isn't that a bummer? All these possible ways to name things. And then to make it even worse, ortho can be abbreviated as what? O. Meta can be abbreviated as M. Para can be abbreviated as P. Do you get the idea that organic chemists didn't know what they were doing when they were doing it? Exactly. They had no idea the stuff that they were playing with until later. And so those common names stick around right? Whereas later on you can develop a more systematic naming system, but everybody knows the old names, and they don't go away. They just stay there, right? Mm-hmm. But hey, somebody's got to do stuff when they don't know what they're doing, right? In fact, that's what I do most of the time. Sorry. No, all right. Shouldn't say that. You guys have lost all confidence in me, right? Hey, but that's what you got to do. If you only do what you know you can do, you're never going to do anything else, right? Yes? I mean, you always got to be doing something you don't know how to do. So you can figure out how to do that. Then you're on to doing the next thing you don't know how to do, right? Boy, if you want a job where you only do what you know how to do all the time, boy, that's going to be a pretty bad job, I think. All right. No, is that what you want? All right. Okay, we need to move on here. We'll lose track of what we're doing. Okay. All right, how do we name this thing? Okay, para-chlorofluorobenzene, you could call it. Or you could call it 1-chloro, what? 4-fluorobenzene. Yes? Mm-hmm. Right? Or you could call it, what do you call the one on the right? This guy. You could call it meta-dibromobenzene. Or you could call it 1,3-dibromobenzene. Yes? Okay? All right. So all cool things there. Yes? All right. Okay. So, handout. Right? Look at the handout here. Let's review some of the alkane stuff. Sorry, you guys, I missed something there? Okay. All right, let's go through this. This is old chemistry now. Yes? And we'll do some new chemistry. All right. So old chemistry, complete and balanced. CH4. Is that an ane, an ene, or an ine? It's an ane. So you have to recognize who you have. Okay? And then you're adding Cl2, and this is a catalyst that allows you to do substitution on anes. Yes? So we substitute one of the H's, right, goes away. And so we have 3 H's. And now we have a chlorine. What happened to the other chlorine? Yep. So we put that with the hydrogen chloride there. Yes? Or you can call it hydrochloric acid. Either way. Now this guy, C2H4, what's he? An ane, an ene, or an ine? He's an ene. If you don't know, draw him out. Okay? There's the hydrogens out there. Yes? After you draw it out a couple times, you'll remember. Okay? Now he's an ene, and we're adding Cl2. Do you need any catalyst? Nope. Don't need any catalyst. It'll just add all by itself. Yep, this part will open up. That part will open up. We'll get a chlorine here and a what? A chlorine there. Yes? So you end up with this dichloroethane. Right? Yes, are you with me on that? Okay. Here we have another one of these ethenes, but we're adding what? Hydrogen. So instead of chlorines here, we'd have what? Hydrogens, and we would have just ordinary, normal ethane. Yes? Right? Are you with me? And then this last one, here we got ethene and what?
Hydrochloric acid.
Hydrochloric acid. So that's going to give me H on one and what? Cl on the other. And all these other guys are H's as well. So that would be a what? How would you name that? Oh, not di in here. There's only one. Right? No, you don't have to say mono. You can just say what? Chloroethane. Do you have to say 1 or 2? No, because both ends are 1. Yes, whichever put that chlorine on will become 1. Yes?
How are there 5 hydrogens now and there are only 4 to begin with?
5 hydrogens? Yeah, one came from the hydrochloric
Oh, I
acid.
see.
Yeah, and it's across the double bond. So the H and the Cl add across the double bond. Yep. So this H is from there. Good question. Yep. Yep. All right. And there's one more to go here. Yes? Okay. We got this thing here. What is this? That's propene. Yes? All right. So again, you got a double bond. And you have HCl. Now you got to decide, does the H go to that carbon? Or does the H go to the inside carbon of the double bond? Because they're not the same now.
We're just balancing these equations. We're supposed to.
Yeah, you are supposed to. You got
How did you get whatever from that little picture?
from what? This?
Yeah.
This is propene? You have to recognize that this is propene, right? Carbon, double bond, carbon. There's H's out here. Yes? And here's the other methyl group out there. And there's going to be an H there. Yes? So every end is a carbon. Every bend is a carbon. And every end is a carbon. And carbon needs 4 bonds. So if it doesn't have more bonds than carbons, the rest of them have to be what? Hydrogens. Yes? Okay. So here it is. And now we're adding HCl. So does HCl come in like, oops, that's not a very good Cl. Does the Cl add here and the H there? Or does the Cl add there and the H here? Okay, everybody's saying yes. Why is that? The rich get richer. Yes. Okay. So there you go. And so then this looks like HHH, right? Carbon with a chlorine on it. Okay. And you got the other H's out here. You want to draw all the H's out there. There'd be an H on this guy as well. And all these guys would be H's. What would we name that thing? The propane. It's a chloropropane. 2-chloropropane. Okay. Cool. Yes?
Why does the bottom one have 3 now?
This bottom one here? It always had 3.
It was saturated.
Yeah. So he's only got 1 bond for carbon, so the rest of them have to be hydrogen. Yes? So wherever you don't see things, hydrogens are there. The hidden hydrogens that Isaiah was talking about. Hidden treasures. Yes. Okay. All right, so here's a question. Oops. If you add to an alkyne, remember an alkyne has how many bonds? 3. If you add 1 Cl2, what are you going to get? You're going to get a Cl and a Cl. And how many bonds will remain? 2. So if you add 1 Cl2 to an alkyne, you get a alkene. What if I added 2 Cl2s? Yeah, then you get a Cl here and a Cl there. And that second bond would go and you'd have an alkane. Yes? So each time you add across a double bond or a triple bond, you're taking one of them away. Yes? If you got a triple bond, you can do it twice. If you got a double bond, you can only do it once. The second time, you break it. Yes? All right. That'd be an alkane if you added 2 of them. Yep. All right. Now, let's talk about aromatics again, because that was old stuff, right? Let's go to the new stuff. So take a look at this. Here are 2 new reactions. Oops. These 2 are new reactions for you. Okay? Right? And what they do is they put chlorine on the ring using iron chloride, or they put a methyl or an ethyl or a propyl on the ring using the aluminum chloride as a catalyst. Yes? All right, so it's a substitution reactions. It takes an H away, because remember, all these guys have what's on them? H's all the way around the ring. So we take an H away, yes, with the chloride, and we put the other thing on the ring. Now, with these new reactions and the old reactions on the other page, the other side of the page, what is going to happen in all these situations? You ask yourself. Here you got chlorine and light. Chlorine and light does what? Go back to the other side. When did you get chlorine and light? What happened? You did substitution of a what? Alkane. Yes? Right? Is there an alkane part of this molecule? This is the alkane part of the molecule. This circular part is the aromatic part. Right? It's not going to react like the alkane does. So, if you have light and Cl2, the alkane is going to react with a substitution. So you get Cl carbon, and you still have the other H's on there, so H2. And you have your benzene ring still as it was before. Right? Yes, are you with me?
Does it have to be HCl?
Oh, and there's another HCl floating around outside there as a byproduct. Yep. Yep. Okay. Now here, we've got chlorine, and we have this catalyst. Ooh, we see the catalyst up here. What does the catalyst do when you add chlorine to an aromatic ring? It puts it on the ring. Yes? Right, so here you have an alkane part. Is this catalyst going to do anything to the alkane part? No. It's going to work on the ring part. Yes? So the chlorine now is going to go on the ring. So let's draw this thing out. Here's my ring. Here's the methyl group still out there. And now the chlorine is going to go on the ring someplace. You don't know where. So you just draw a line to the middle there and say chlorine. Yes? Could be on any one of those other carbons other than the carbon that has the methyl group. Yes?
So if they don't know where, we just put it in the middle?
Yep. No, this other one is a CH3, remember? Yeah, but what does the other chlorine pick up? The hydrogen that it took away, yes? So that's the byproduct, HCl. All right, I know this is getting a little messy. Now you have Cl2. Is there any catalyst indicated?
No.
No, so can it go on the ring?
No.
No. Can it go on an alkane part?
Yes.
No, it can't. You need a catalyst for an alkane part. You need the light. Yes? No light, you live in the dark. Yes? All right. So what can Cl2 react with all by itself without a catalyst?
CH2.
Yeah, it can add to the ethene part here. Yes? Can't do it to the ring, even though there's double bonds in the ring. The ring behaves like a ring. Okay? So it has to add to this part. Okay? So what are we going to get then? Let me draw it out here on this side because that side's getting messy. Yes? So we got our carbons, and we're going to get a chlorine there and a chlorine there. Yes? And I can put a little circle in my ring to put all the double bonds in there. Yes? So that's all that can happen because there's no catalyst. Yes?
So if you if you break a double bond.
Yeah, it would be just like alkene reactions. So all these things you have to look at the reagents, ask yourself what can the reagents do? Yes, and then look at the molecule and ask yourself what parts of the molecule can react that way.
So
Yes?
where's the CH2 go?
CH2?
Yes.
The CH2 is still, the hydrogen is still there, right? I just didn't draw them in. Okay, but you realize that they're still there.
Have to draw them in.
No, you don't, because you know that they're there. They're the hidden hydrogens that Isaiah was talking about, remember? Yeah, if you need more things, you just put hydrogens in there. Remember, carbon needs to have how many bonds always? 4. Okay? So if it's only showing 2, that means the other ones are what? Hydrogens. Yes? So since we assume that you know they're going to be there, we don't have to draw them. You just know they're going to be there. Yes? Okay. All right. Okay, which one? Okay, last one here. HCl. What's HCl going to react with? Can it react on the ring? No, there's no catalyst. Can it react with some alkane part? No, there's no light. Okay? So it's going to react with the alkene part. But now we have an H and a Cl. Who gets the H and who gets the Cl? The rich guy gets the H. Yes? And the Cl goes on over there. Okay? So again, you draw your little benzene ring. Yes? Chlorine goes there, and you just draw it like that. Yes? And now you realize that that end carbon has how many hydrogens on it? 3. And you don't have to draw them out. Just realize that they are there. Yes?
Yes.
Just know that they are there. All right. Okay. Whew. Can we do all this? This is like Spanish class. First, they teach you how to say your name, right? But then you get a whole bunch of sentences and you have to put in a conversation. No. It's not like Spanish class?
Then they expect you
Oh,
to have a
this.
full conversation with your teacher.
That's right. So we're going to have a conversation in organic chemistry here. All right.
Oh, that sounds weird.
So,
We just don't know what they are.
all this, if I can get you back here, okay? All this aromatic stuff we went through nice and slow so you could see how it works. Yes? Now, for each of our subsequent functional groups, we can go through this so much faster because you know what to do. You need to know the physical properties, you know the nomenclature, and you need to know the reactions. Okay? All right. So here we go. Let's go through alcohol, carbonyls, ethers, and amines in 5 minutes. All right. Yep, so here they are. Remember your functional groups here. What is an alcohol? It's got an OH on it, yes? What is an aldehyde? It's a carbon doubly bonded to an oxygen. You guys were supposed to memorize these way back when already. Yes, I told you that. They were good quiz material. You got to listen to me. I'm not faking it. All right? Yeah, so here we go. Let's see if we can name this alcohol. Right? Yeah, name the alcohol. That's the name of the game here. Name the alcohol. All right. Okay? So here's the alcohol. That's the alcohol functionality. Over there's an alkene functionality. We still got to find the longest chain. Where's the longest chain? This is here. It's outlined for us. Okay? Now we put the lower number on the alcohol rather than on the alkene because an alcohol is more important than an alkene. Yes? How do you know that? Because I just told you. Okay? And there's a list of these things in the book, the chemical research book, right? Yes, TRC handbook. All right, now alcohols are named with an O, right? So this is going to be 1, 2, 3, 4, 5, 6. So it's a hex, right? A hexanol would be the alcohol, but it's also a hexene. So it's a hexenol. Exactly, you got it. And then you got the substituents falling on it, right? There's a methyl and an ethyl, right? So it's going to be an ethyl methyl hexanol. You just got to put the numbers on there. That's all. This all makes perfectly good sense. It does. It follows the rules. Right? 4 ethyl, 4 methyl.
Okay, explain.
Hex what? Hex 5E, hex 3 all. He's got it. We said to put the numbers in there.
Where'd you get the 4 ethyl from?
Well, 1, 2, 3, 4. Here's the other group. Carbon number 4.
I thought it went to 6.
Yeah, it goes to 6, but the ethyl is on carbon number 4. So it's 4 ethyl, yes. And it's also, here's a methyl group on carbon number 4, 4 methyl, hex 5 ene, because the ene starts at carbon number 5, and the alcohol is at carbon number 3.
You had like a 50 miles per hour.
No, this is like, 15 miles per hour over the speed bumps. You know how to do all this. You do. You've done it before. You just got to do it at the same time. That's all. It's like playing the left hand and the right hand.
It's very hard.
No, it's fun. All right. Okay. So what's this alcohol going to be named? This is easy. This is what? 1 carbon, so it's meth. Methanol. There you go. Okay. What's that going to be named? Chloromethane. Yes, you guys got it. And hydrochloric acid there, or hydrogen chloride. Either way. Okay, now what we have here is a nucleophilic substitution. Okay, so this is what you think to yourself. The rich attack the who? The poor. Okay, and if you look at HCl, who's going to be richer? The Cl or the hydrogen? No. The Cl is more non-metallic. The Cl is going to be rich. Yes. It's going to attack the poor because which of these guys is richer? The O is richer than the carbon. Yes. So rich here. Yes. Rich there. Yes. This rich guy attacks that poor guy. Okay. And this rich guy attacks what? That poor guy. And you see what happens? The chlorine ends up on the carbon. Yes. And this H and the OH end up as water. Why? Because the rich were attacking the poor. Yes.
Is it safe to say that hydrogen is going to be poor?
Depends who hydrogen is with. If hydrogen is with oxygen, oxygen is a lot more non-metallic than is hydrogen. So oxygen is going to be the richer partner here.
You're saying it's rich
Because it's further to that side. Yep. Further to its non-metallic behavior. Fluorine is the richest, the greediest of everybody. Yes? Mm-hmm. Okay. So remember, who attacks who? The rich attack the poor. If you follow that, it always works. It always works. Okay? Mm-hmm.
So, there are 2 rich and 2 poor. How do you know which one attacks which?
They both attack each other. The rich part on this one attacked the poor part on the other one, remember?
There's three things.
This rich one attacked that poor one,
Why didn't
right?
it attack the other
This rich one attacked that poor one.
CH3 and the OH already bonded, that's what the line is.
Yeah, these guys are already, this is a molecule here, right?
That was what I
Yeah.
was missing.
Oh, okay, yeah, that's one molecule. Yeah, yeah. Yeah. They're just trying to emphasize that this bond here is going to be breaking. See, that's the idea there. Okay. All right. Now here's some more fun stuff we can talk about here. Here you have a single bond. What do we have over here? A double bond. Yes? Because what happened, this O, who is rich, attacked the hydrogen of the acid, who is poor, pulled it off, made a water, and left. That's the story. Rich attacked the poor, went on its own way, like the cow that jumped over the moon. Okay? Okay? So, there we go. So, take two hydrogens away, yes, and alcohol becomes this thing. What's this thing? This is a aldehyde. Yeah. Alcohol goes to an aldehyde if you take hydrogens away. If you take hydrogens away from an aldehyde, what does it become? Looks like Ku, but it's not. Okay? It's a carboxylic acid. Yeah, this is a really bad way to write a carboxylic acid, but that's how they do it, right? Okay? So, now, look here. How many oxygens does this carbon have a bond to? One. How many bonds does this carbon have a bond to oxygen? No, two. Double bond. Carbon, oxygen, double bond. Yes? You got to be able to draw this out so you see the structure of it over there. Now, this carbon, how many bonds to oxygen does it have? Three. A double bond and another one. You have to know these functional groups. You have to know what an aldehyde is, what a carboxylic acid is. Yes? Uh-huh. Yep. You just got to know them. And you have to know. So if you go up in bonds to carbon and oxygen, you are oxidizing the carbon. 1, 2, 3. We say this carbon is more oxidized. That one is less oxidized. Yes? You take hydrogens away and make more bonds to the oxygen, you're oxidizing it. And you can go up the chain or down the chain. Yes? You can oxidize an alcohol, it becomes an aldehyde. Oxidize an aldehyde, it becomes a carboxylic acid. Yes? So you can choose what you want to do your next step. So this is going to become like a 16-step chess game. Yes? Now, what do you know about water? Does water react with sodium? Yeah. What is water? Water is a substituted alcohol. Yes. Water is a substituted alcohol. So that means water and alcohol are similar to each other. Water reacts with sodium. Alcohols are going to react with sodium. Yes? Now don't you go to the corner cafe and say, oh, Dr. DeBoer said that, alcohols are just substituted water, so just give me some of that substituted water there. That's not going to fly at the corner cafe.
Different kind of alcohol.
Yeah.
That'll kill you.
Yeah, you want the ethanol, actually, with more carbons on there. Yes? All right. Anyway, here we go. Now, here, rich and poor. Let me tell you about the rich and the poor. Okay? The rich are what color? Red. The poor are what color? Blue. So, this is formaldehyde. That's the common name for this aldehyde right there. Which part of the molecule is rich? The oxygen part, the greedy part, the non-metallic part. Okay? Here you have acetaldehyde. It's another aldehyde, but it's got a methyl group on it over there. So again, the oxygen part is what? Rich. And so they draw these rich and poor things out there in your book so you know which part of the molecule is rich, which part of the molecule is poor. Yes? Who is going to attack who? It's very helpful to know who is rich and who is poor so you can draw the arrow from the rich to the poor. Okay, and follow out what happens when the rich attacks the poor. So remember, rich is red. Yes? Poor is blue. R goes with red. P doesn't go with blue, but that's too bad. Okay. All right. So that's why they have these pictures in your book. Because it's important to know who is rich and who is poor. The rich ones are going to be the what ones on the periodic table? Yeah, these guys up here are going to be more rich. These guys further down in the non-metallic things are going to be the poorer guys. And if you've got poor old metals, I mean, they're big time losers. Right? Yes. Right. So know who's rich and who is poor. And we'll be good at these things. Okay? All right, so let's talk about ketones. Right? All right, all kinds of ketones. You guys use these all the time. Ketones occur naturally. You eat them in pistachios. You put musk cologne on your guys, you know, and that's a ketone, right?
So the red ones are rich?
The red ones are oxygen in this case. Yeah, yeah.
But yes,
Yes.
oxygen will be rich.
Oxygen will be rich. That's why they make them red. Yes, which makes good sense, right? Okay. All right. So let's talk about reactions of alcohols and aldehydes. I still got 3 minutes here. Yes? Yeah, and you don't want me to do it more of it tomorrow, right? So let's get it done. Okay, so how many bonds between carbon and oxygen here? 1. How many bonds between carbon and oxygen there? 2. So who's more oxidized? This one is more oxidized. What is the functional group here? It's an aldehyde, which is why it's called an F-N-L. L for aldehyde. Yes? Whereas this thing is an F-N what? All. It's an because it's all single bonds. It's an all because it's an alcohol. This is an N because it's single bonds. It's an al because it's an aldehyde. Yes? That's a double bond, and not between the carbons, though, but between the carbon and the oxygen, which makes it an aldehyde. Yes? Okay. Well, if there are 3 carbons, then it would be propanol and propanal. Aldehydes are always on the ends. Yes? Because you need to have the hydrogen out there. So aldehyde is always going to be on the end. Okay. So I can oxidize an alcohol, right? And it goes from 1 carbon-oxygen bond now to 2. Now this was an all. What's this thing over here? Yeah, an one. What is the one group? The ketones. Yes? Uh-huh. So I went from an alcohol here to a ketone. If this thing was at the end of the molecule, if there's an H over here, it'd be an aldehyde, but it's not the end. It's in the middle. It makes it a ketone. You've got to know those functional groups. Yes?
Two H's go.
Yeah,
Where the 2 H's go? They just went off to wherever the agent was here that was oxidizing it. Yeah, lots of different possibilities there. Okay? So we're not so concerned about the byproducts here as we are with what we're doing up and down the ladder.
The O's, not the H's.
Yeah. Yeah. Well, we're concerned about the hydrocarbon part here. Yes?
And then oxidation makes it a double bond.
Yes. Yes. And if you oxidize it still further, you could place this thing with an OH. Yes, and then you'd have 3 carbon-oxygen bonds. Yes? Right? You can keep going up the ladder. Or down. It is hard work. Okay. So here we go from an on to a what? To an all. We went down. You go down, it's a reduction. Down in the number of carbon to oxygen bonds. Okay? That goes down from a ketone to an alcohol. Yeah. You got it. Yes. And again, it's a butan on and a butan what? All. And 2, because it's 1, 2. Yes? It all just follows the rules. Right? The nomenclature is easy once you get the hang of it. Right? It is. And I still got a minute. All right. Okay. So, here is a good example of the rich attacking the poor. So, look at this. Yes, here you go. All right, you're with me here, right? You know about this, right? All right, you're with me. All right, you're down with this. Okay, so who's rich on this molecule? Oxygen is rich. Okay? Who is the poor guy then? Yeah, this end of the molecule. Okay? Now, look at this thing over here. H here is poor. Yes? And this thing here is rich. So rich attacks the poor. Rich attacks the poor. And what do you get? This thing over there. All because the rich attacks the poor. Okay. So what do we remember from today, class? The rich attack the poor. All right. What's it take to be a chemist, class? Hard work. Hard work. Okay.